Hello and welcome to part 2 in this video series on the Arduino Zero speed test. In the last video we compared a built-in function, analog write, to a custom or optimized function, and we saw we got a significant improvement in output frequency. In this video we're going to continue to see how we can increase the output frequency by conducting a few speed tests, and then we'll see the results from those modifications as well. I see that from the principle of operation, a conversion is started when the data is written to the DAC data register. There's some conversion time, and then there's a voltage output. So if we can remove any unnecessary sync DACs, then we can improve this timing of this output and make it faster. It's a little challenging based upon this data sheet because we don't have a detailed timing diagram. For example, here's a digital to analog converter by Analog Devices. We don't have the luxury based upon the datasheet for the microcontroller, so we'll have to do some experimentation. Here's a summary of the results so far. We had the built-in compared to the first speed test. In the second column, we have the code reference so we can see how we modified it relative to the previous value or other values, and then the output frequency. And we see just by taking out some overhead from the previous built-in code, we improved by 2.2 kilohertz. We'll add to this by removing sync values to see if we can manipulate this to get a valid output that's faster. The datasheet specified that once the value is written to the data register, the conversion time starts. So I figured, well, in this loop, we iterate through this code. We assign the value, we sync. We assign the value to the data register, we sync again, and then we write it to the control enable, which provides the output. So when we're looping through, we would hit the sync DAC at the bottom of this code here, the last sync DAC. Then the loop would start over again. We would hit value and then do another sync DAC. So I figured, let's comment out this sync DAC, which is equivalent to removing it from the code, and see what happens to the output. Here is the resulting output from this code. We see that the frequency output is 4.0688 kilohertz. Here are the results summarized so far. So in speed test 2, we removed the last sync DAC from the speed test 1, and we got the 4 kilohertz output. The change from speed test 2 to 1 was an improvement of 470 hertz, which is pretty good. My next test was to remove the sync DAC following the value assignment. That way we're only checking the DAC status after we assign the value to the data register. This results in a 4.798 kilohertz output frequency. We can see that from speed test 3 to 2, we got an improvement of 730 hertz. The last speed test was to remove all the sync DAC functions. This is more out of curiosity to push the limits to see how fast this code could go without checking the DAC status. See, we have an 8.9 kilohertz output frequency, which is a real significant improvement between the last test. And comparing speed test 4 to 3, we see there's a 4.11 kilohertz improvement, which is the largest improvement between tests of this bunch. And so far, we've only looked at the output frequency as the measure of these tests. I decided to take a closer look at the waveforms to see if I could find any errors or any anomalies based upon the output results of my oscilloscope. We'll first start with the control sample of the built-in function. As we get closer and closer and we can see the actual stair-stepped like DAC writes, you can see nice stair steps that are clean and there's no gaps or delays in between. There's a little bit of noise, but that's to be expected. And you can see here I added a column on the right, errors in output. This is the first delay test, and you can see I started to notice that when I would do stop triggering here, I'd just take individual screenshots. Every once in a while, I'd see these anomalies here. And I'm zooming in to see that there's actually at least one value of error that I'm detecting. Notice how this stair step, so to speak, is longer than the other before it and after it. And here's a visual to see. So the DAC is writing, but then it seems to stay output at a previous value, holding it for at least one sample over than what we would have liked it to. Now that doesn't happen periodically, and it seems to happen kind of intermittently. Here's the summary table with speed test 1 added. You can see here I put the value that the errors and output writes was about 1 because it held one value for too long. Now let's take a look at speed test 2. So here I'm just taking individual shots here as opposed to free running, and I started to detect the errors as well. So notice our output frequency increased because we're doing speed test 2. And again, these weren't periodic, meaning it wasn't a fixed error, but it would happen intermittently. Here's a closer look at speed test 2. Note that the results are similar to speed test 1. Here's speed test 3, and I did the same procedure where I'd start and stop. And here's a zoom in, and it's about the same phenomenon here. We get about 1 DAC output value of error. Speed tests 1, 2, and 3 all had very similar errors in terms of duration and frequency. Now let's go ahead and take a look at speed test 4, which will be where I removed all the sync DAC functions. And I found that these errors happened a lot more frequently in this one. And they were actually more prominent, as you can see. Here's a closer look at the waveform with the error projected. As you can see, there's more error in this speed test than the others. There's actually 3 DAC output values worth of error. And that's to be expected because here we're not really even checking the DAC status. So there's definitely trade-offs here. And it really all depends on your application and what you're trying to do. If the fidelity or the quality of your output wave can have a few errors intermittently, but you'd rather have higher frequency, then this actually isn't too bad of an option. It was difficult to determine the exact cause of this problem because the datasheet doesn't give us detailed timing. However, I did pull up the datasheet, and my suspicion is that the bus is stalling, and that's why the output is held. I read here, if an operation that requires synchronization is executed while status sync busy is 1, the bus will be stalled. All operations will complete successfully, but the CPU will be stalled and the interrupts will be pending as long as the bus is stalled. Recall that the sync DAC function is simply checking status bit sync busy. And this is what the datasheet is referring to in the sync busy, and that's why we check it. Thank you for watching this video, and I hope you've learned more about how you can optimize your Arduino Zero DAC writing functions. We see here some pros and cons in the summary table of the results. Stay tuned for more content, and let me know what you think in the comment section.